Okay, so it's my pleasure to introduce today's speaker, Khoa Nguyen, from University of Calgary, and he'll talk about D-finiteness, rationality, and height. Yeah, please.
Right. Yeah, so I wish to thank the organizers for the invitation. Today I'll talk about D-finiteness, rationality, and height. So, so D-finiteness is a property about power series. And when you consider the power series to have algebraic coefficients, then it turns out to have certain strong arithmetic properties. And well, and there are some surprising related results in other areas that when you look at the result that I'm gonna tell you at first, it doesn't seem that somehow there's surprising connection to other problems. All right, so let me start with the next slide. Um, so there's a general theory of way height on for points, algebraic points on algebraic varieties. Um, so it involves, divisors and so on. But for today, we only need the so-called absolute logarithmic way height on a Q bar. And this is a very simple, well, easy to define function, um, as you will see. So in general, in order to define a height function, you need to compute, you need to combine all the contributions from all the absolute values, like all the Archimedean and all the periodic absolute values. You have to combine them to define your height functions. But in this case, there is an explicit formula. So let me tell you what it is. So you consider the minimal polynomial of your element of your number over z. Um, so this is your minimal polynomial. So C is just the GCD of the coefficients. Take it out. Hold on, let me see. No, I'm sorry. C is the leading coefficient. And then when you take it out, you have these are the roots of your minimal polynomials. It's just a Galois conjugate. And then the height is going to be 1 over the log of absolute value of C plus sigma of this quantity.
But can it just cancel C? I mean, so the all if I take C being one, to be also the minimal polynomial, right?
No, yeah, this is a minimal polynomial over Z. It's not over
Ah,
Q.
okay. Sorry. Thank you very much.
Yeah. So, well, for example, all right, hold on. If you have a rational number a over b, then of course the minimal polynomial over z is going to be bx minus a. You take b out, it becomes x minus a over b. And then it depends on whether it is bigger than 1 or not. Uh, so, so it depends whether the absolute value of a bigger than the absolute value of b or not. So your the end result is going to be this quantity log max of absolute value of a, absolute value of b. And one consider this as some sort of arithmetic complexity of your algebraic numbers. So if you have a bigger height, it means you are more complex than number with a smaller height. Um, and again, in a certain sense, people also think of this as the number of digits required to express your number, because, well, you write like this, and it is pretty much the maximum of the number of digit in here or in here. But of course, this is an easy to give definition, but in order to prove certain properties, well, to be honest, it's better to use the other definition that I don't mention, that you have combined the various absolute values of your field. So that is actually more conceptual definition. Anyway, so let me move on to the next slide. Right. For example, if Px is a polynomial of degree D, oh, I should say this Q bar. You can consider polynomial with algebraic coefficients. So that is Q bar. Then the height of P alpha is going to be D times the height of alpha plus something that you can control independent of alpha. Well, plus something that you can give an upper bound that is independent of alpha. The point of this is that it is true for every alpha. So this constant is independent of alpha. This the upper bound here. So this means, as I said, there is a positive C depending only on the polynomial, such that the height of P alpha and D times the height of alpha is less than or equal to C for every alpha. So in particular, if you have a polynomial and you look at the sequence Pn and in Z, then the height is more or less D log n within a certain controlled error. Okay. All right, so now let me talk about the finite series. Again, n naught is n together with 0, and n is a set of positive integer. So k is a field for now, but later on we'll consider k to be a Q bar. And m is a positive integer. So we consider this bolded n is a tuple of n1, so on, and m. And this vector x is a vector of indeterminate x1, xm. Because I'll write x to the n to denote the monomial, x1 to the n1, so on, xm to the nm. And the norm of this is the sum of the ni, so it's the total degree. And of course, in calculus, this denote the operator, which you take partial with respect to x1 and 1 times, and so on, partial with respect to xm and m times. On this power series in m variables, so we can take this operator. And now, so we say that our power series is D-finite over the rational function in m variables if only the partial derivatives span the finite dimensional vector space over that field rational function. Well, some people also call these, well, at least in one variable case, they call it a holonomic function. So again, D-finite and holonomic the same. And from now on, we work with the algebraic numbers. So we let k equal to Q bar. And this is our goal. We consider a D-finite power series in m variables, something like this. And we study the role of the height of the coefficients with respect to the total degree, so the norm of this, so the degree of the monomial. So I'm going to give you some explicit examples soon. But this is the kind of problem that we consider. And there's a general heuristic that is not just in my talk, but pretty much in many other places in number theory. So when there is an interesting algebraic or geometric condition, for example, you have the D-finite condition, or if you consider other kind of equation, difference equations, or Mahler equations, then it's also an interesting algebraic condiction. Then there should be an interesting constraint on the arithmetic of the object. So for example, in this case, we consider the role of the height of the coefficients. Okay. All right. So any questions so far? All right.
No, everything's great. Yeah, thank you.
Okay, thanks. Yeah, if not, then I'll continue. Okay. And again, to get to get the feeling and the idea for what's going on, it's perfectly fine to just consider in the case of one variable. So now we have a one variable D-finite power series algebraic coefficients. Then we rely on the partial derivative. Of course, in this case, there's just one variable to span a finite dimensional vector space. So it's the same as requiring this guy to satisfy a linear differential equation with coefficients in this polynomial. Well, in the field of rational function, but you can clear the denominators, so it doesn't really matter. And if you have a linear differential equation like this, you write down the equations, you setting the coefficients to be 0, you expand everything out. You eventually you have that. So equivalently, the coefficients satisfy a linear recurrence relation with polynomial coefficients. So it's different from rational functions when the coefficient satisfies a linear recurrent relation with constant coefficients. In this case, we do have polynomial coefficients. So we have a linear recurrent relations of this form. So for different n, you have different relation because these guys they change. Okay. Yes, so that's one way to think about it. And now I'm going to give you explicit examples together with the rho of the height of the coefficients. All right, so of course we first one can consider the exponential function. So sigma x to the n over n factorial. In this case, the height of this coefficient 1 over n factorial is the same as log n factorial, which is more or less n log n. Okay, so this is a kind of this one kind of function that can appear as the rho of the height of the coefficients n log n. So next, we can have rational function with at least one pole not being a root of unity. So for example, this guy has a pole that is 2. It's not a root of unity. And when you expand this out, of course, it's sigma 2 to the n, x to the n. And the height is n log 2. So it's a linear function in n. In this case, it's a linear function. The next example is a logarithmic function when, well, again, here it is first year calculus. So you to get this power series and the height of an is log n. And I want to emphasize that we have this function as a rho of the coefficients. All right, so now let's talk about the next two examples. Oh. So this one, the rho of the height is also more or less log n. But it's different from the previous one because first of all, it's a rational function. The previous one was a transcendental function. This guy is rational. And you can notice that this guy has, although all the poles are roots of unity, in this case 1, but the order is at least 2. And so you have the height is around log n. And finally, in the last example, this is the case when all the poles are roots of unity and they have order 1. For example, well, denominator is 1 minus x 2020. Well, I guess I should change this into 2021, new year now. Anyway, so it has, if you have something of this form, then it is actually the case that the coefficients belong to a finite set. And again, belong to a finite set is actually the same as saying that your coefficients have bounded height. There is a Northcott principle that if you consider in a fixed number field, then there are only finally many elements of bounded height. So again, in this case, the rho of the height is O1. So in conclusion, you see that you have this kind of function, so you can have something like n log n, n, well, so something times n. So and then log n, and then O1. So these are the possible row of height, at least according to these examples. And the result that I want to tell you is that at least there's nothing in between these guys. So if you are smaller than log n, then you have to be bounded. That's the kind of result I want to tell you next. Okay. All right. Yeah. So I'm more of a problem solver. So let's see an interesting problem that I can solve. I'll try to do it. And this is well, as you will see, this is the story about a small and, well, to clarify, the small and unimportant problems are from me, but the highly interesting results and more important are from other people, as you will see. And this includes a recent solution of the Schinzel-Zassenhaus conjecture from the 1960s by Veselin Dimitrov. So somehow this motivates that one. It's quite amazing. But let's start with a result of Jason Bell and Xiaoxi Chen in 2017. So here's the result. So you have a D-finite power series in m variables. Well, to be fair, their result, they don't just consider algebraic coefficients, they consider, so they replace this by k, where k is any field of characteristic 0. But it's not important because you can do specialization. So you can reduce it to Q bar, it's fine. So let's just say that this guy has algebraic coefficients. Now, if the coefficients of f belong to a finite set, then f is rational. So that's the conclusion. So when I saw this result, my first impression is that the assumption of the coefficient is too strong. So you require the coefficient to be belong to finite set. It seems a very strong condition, and the conclusion is that f is rational should also be stronger, because if you look at the previous examples, not every rational functions give you that the coefficients belong to a finite set. Only those when the poles are roots of unity and what is that? And the order is at most 1. So the order of the pole is 1. So we should be able to relax the condition and strengthen the conclusion. So that's what I thought. And as mentioned before, if you look at the previous 5 examples or the first 4 examples, you see that the height of the coefficients, well, at least in one variable D-finite series, they draw as either n log n, or log n. And then after that, they are all one. And my goal is actually to replace the assumption that this guy belongs to a finite set by the condition that is dominated by log n. So again, my goal is actually to prove that there's nothing in between this and this. Yeah, so if you are strictly smaller than this guy, then you have to be here. That's so like there's a gap in the row of the height. So in this direction, when I think about this, in this direction, actually there was a related result by Van der Putten and Spalinsky in 1996. So what they prove is they consider power series with rational coefficients. And actually they prove that the height of the coefficient cannot be strictly in between log n. So if the height is smaller than log n, then it has to be in here. So that's what they prove. And what we are about to prove is, first of all, is for multivariable functions. So this guy consider one variable function. We consider multivariable, and we improve this to log n. Okay. Let me erase all these. Okay. So now we consider an m variable D-finite power series with algebraic coefficients. And when I started on this, I proved some initial results, and then with further discussions with Bell and Zanier, we have the following. So this is our result. We assume that the limit of the height of an over log n, well, log of the total degree here, the norm, is 0. So it's dominated by this function log n. Then the first conclusion is that f is a rational function. And I want to get to that the height is 01 at the end. So we have to work more on it, and then as those examples, we realize that the denominator. So if f is not a polynomial, so if the coefficients don't eventually become 0, then the denominator, well, up to scalar multiplication, it has the form. So the product of 1 minus zeta I x to the ni. So this guy is a root of unity. And this is a monomial x to the ni here. And these are all distinct. So these factors are distinct. So it's similar to in the one variable case when the order of the pole is at most 1, is 1. So it actually has very restricted type of denominators, and the coefficient, finally the coefficients belong to finite set. So again, the goal is to show that if you are strictly smaller than log n, then you have to be 01. So that's the goal. All right, so I guess let me just talk very briefly about the proof. It turns out that the proof of this is actually not hard. It's quite simple. You use the basic properties of height. The proof of this is actually a lot more tricky. Actually, both of these B and C is tricky, and we use some Diophantine geometry here because if you look at the variety defined by this denominator, so if you look at this, if you set this equation to be 0, then it's actually a translate of an algebraic subgroup of tori, right? Because the zeta I is a translate. So we look at the set of points for which the denominator vanished, and we play around with it, and then eventually we conclude that it has to be of this form because it's a translate of subtori. Okay, so that is one result in our work. Okay, and you can forget about that. The point is that there's a gap in the row of the height of the coefficients. If it's dominated by log n, there is O1. So it cannot be log n or anything in between. So that's the point. And well, that's sort of the main result. In that paper, we also prove that if you consider one variable case, we also prove that it cannot go beyond n log n. This is the example of the exponential function n log n, and it cannot go beyond that. But well, the other one is the main result. You can think of that. Okay, so if f is, so let me talk about further results after our work. So if f is not rational, then we have lim sub of a height of an over, oh, this is log n. There's a typo. It should be log n. Yes, of course. It should be log n here. All right, so at least in the unit, in the one variable case, it looks like, well, the best or the worst, if you, depending on the point of view, but look at the extreme case we can do is something like this function, where k is a fixed positive integer. So this it's not rational, and the coefficients look like this. So the coefficients here, height of an is log n minus log k, if k divides n and there's 0 otherwise. And in our current work in progress, we prove that is indeed the best possible scenario, or the worst possible scenario, like the smallest possible height you can have for a D-finite non-rational function. So if f is D-finite and the coefficient is in Q, so it's also a quiet PT here. It's D-finite and irrational. Then we have that, previously we have lim sub of this divide this is bigger than 0. But now we do have that actually that lim sub is actually greater or equal to 1. So we do have that height of an greater than log n minus a constant for n in a set of positive densities. If you look at this guy here, n belongs to all the multiples of k. Otherwise, the height is 0. So so we could prove this. Still try to relax the condition that f has rational coefficients. Oh yeah, I actually didn't mention that. So let me mention it. We believe that this is also true when f has algebraic coefficients, but we couldn't prove it for now. Okay. And now let's also talk about further results in arithmetic dynamics. So soon after we release that paper, then there are more work by Bell, Gilkar, Hu, and Satriano about what they call the height gap principle in arithmetic dynamics. And here's a setting. So X is an algebraic variety. Phi is a dominant rational self-map. F is a dominant rational map, so it just means it's not constant. It's a rational map from X to P1. All of these are defined over a number field. And now you look at the orbit, phi to the n of C. Look at this orbit, and you look at F of D. So F is some sort of, so you can think of this as a set of numbers if you ignore the point at infinity. So F is certain value, certain function on these orbits. And for D-finite one variable function, you can find appropriate X phi Fc so that these an are actually f of phi n c. So you can say that their work is a generalization of our earlier work, at least for one variable function.
Right. So it's like about time. Do you think it's a good time to stop for a break, or?
Maybe I can talk for like 2 more minutes if it's possible. Is it?
Yeah. Okay.
Okay, I'll try to finish this quickly because I want to.
We'll have time after the break, so you can just. I mean.
Oh, okay. All right. Yeah. So after the break, we can continue. Oh, okay. All right. Right. Yeah. So I just mentioned our current work in progress, and there's also other work in arithmetic dynamics. So so these guys they can fit, at least for one variable function, they can fit these coefficients into the framework of arithmetic dynamics when they iterate a self-map of a certain variety. And they have the height gap principle that I guess you can probably guess now. So they propose and they also prove some partial results about the following. So if lim sub of the height of f of the iterates over log n is 0. So if this quantity is dominated by log n, then these guys that appear in the height. So this guy is a finite set. So and you can say this is a direct generalization of at least in the one variable case for D-finite series. Also later on after this, Jason also suggests the following possibilities. Well, according to those 5 examples that I mentioned. So if this height, I should say, I'm sorry, there should be an F in all of these. So there should be F here. F of these guys and F of these guys. There should be all these F here. Okay, I guess you know what I mean here. There should be, you evaluate F at these points. Okay. So if the height of this guy is dominated by n log n, then is it true that it has to rub down to like bounded by linear function in n? If it dominated by n, is it true that it's bounded by something in log n? And if it is dominated by log n, is it true that it's bounded by something by a constant? And this is the same as the above high gap conjecture. So he also has this kind of questions. And next is about a recent result that, well, it's not quite recent. It's around our math last year, I think, but I'm only aware of this very recently. So Adamczewski and Bell, they prove a height gap theorem for coefficients of Mahler function. So again, it is the kind of game that I mentioned last time. If you have some interesting algebraic condition, then maybe you can talk about interesting arithmetic constraint. So they consider Mahler function and the coefficients of these guys. And roughly speaking, they prove the following. Again, it's a similar kind of result. So if the height of the coefficients is dominated by n, then they drop down to log square n, so log n square. And if it is dominated by log n square, then it's around log n at most. If it's dominated by log n, then it's around log n at most. And then if it's dominated by log n, it has to be bounded. So that's what they prove. And finally, the last result I want to talk about is a result by Veselin Dimitrov. So it was also a little bit funny because he didn't pay attention to our work first. There was another like combinatoric paper of me and Jason, and he noticed that paper, and eventually from that paper he noticed the D-finite results that we have. And you know, he asked us about this, and after some discussions, he came up with a very beautiful proof of so-called Schinzel-Zassenhaus conjecture. So they prove the following. So they conjecture the following, and he proved it eventually. So here's the problem. You consider a monic irreducible polynomial with integer coefficients of degree n greater than 1. So now so if you look at the cyclotomic polynomials on the roots, of course, roots of unity, so the absolute value is 1. But as long as you assume that the polynomial is non-cyclotomic, then there is a gap between 1 and the biggest root, the root with the biggest value. So the point is that this positive C is independent of n, independent of all the polynomials. So there is a positive C. And if you read his paper, actually he provides a very explicit C. I think it's like log 2/4 or something. So if you have a monic irreducible non-cyclotomic polynomial degree n greater than 1, then there is a root where the absolute value is greater than 1 plus C over n. It looks very simple, but if you try to prove it, you might see it's quite non-trivial. People actually try to prove this for their case, and eventually he got this. All right, so finally. Okay, yeah, so thank you for
thank you very much for the wonderful talk. So let's thank the speaker. And we have a question in chat. William is asking, is this constant C which you have shown maximal or best possible?
No, it's not. The one he got is not the best possible. People predict a better one, but can I see the chat? Yes.
Yeah, you should be able to.
No, it's not bestable. No, not best possible. But on the previous constant people got, it involves n in it. So this is the first one when it is independent of n,
which is constant.
Yeah.
Okay. Other questions? Just feel free to unmute yourself and ask or type them in chat. Michael?
Hi, it's Michael Singer. I have a question, a few. So are there conditions that guarantee that a power series solution is algebraic, an algebraic function, not necessarily a rational function?
Well, not that I'm aware of for now. Yeah, so it seems that on the conclusion is that if it's special enough, it becomes rational. Yeah, so yeah, that's a good question, and we never thought about that actually.
And then going back to rational functions, so your results say that under a certain condition, the power series is rational but has a very restricted denominator.
Yes.
Is there any hope of somehow characterizing rational functions, all rational functions, by arithmetic conditions?
At least for one variable function.
Yeah.
Then for one variable function, then the coefficients are like something like this: b1n alpha 1 to the n pk and alpha k. So the alpha I are the root, are the poles. Right. Well, at least you can rid off the maximum of the alpha I from the rows of the height of an. So if we only look at the height of an, then I think we can rid off this quantity. I think, but to actually determine all these from, we cannot determine all these from this quantity, I think.
Yeah. Or, I mean, even if it's just order 1 poles. Well, probably there's no difference.
So when you say that these guys are bounded or belong to finite set, you know that all these alpha I actually have to be roots of unity. And
sure.
Yeah. But if you go beyond that, then I don't know. Yeah.
Okay. Well, thanks. This was a really nice talk. It was very informative.
Oh, thanks. Yeah, I'm afraid it's not doesn't involve too much to the topic of the seminar, but
no, it's very good.
No, it perfectly fits.
Yeah.
Fits. There's a question in the chat. Alexei is asking about interesting examples with coefficients which are not in Q. Because most of the examples presented in the talk, all the examples were coefficients in Q. What are your favorite examples with non-rational coefficients?
I mean, in principle, you can have examples that your coefficients are not in Q, but interesting ones, I am not so sure. Even for Mahler functions, is it that a lot of the interesting examples actually have coefficients in Q? Are you aware of? Well, so let's say it this way. There are probably interesting examples where coefficients are not from Q, but I'm not aware of those.
Okay, thank you. There is also example in the chat by John. Hey, can you see the chat, by the way?
Yeah, I can see it.
Okay.
Yeah. Right. So, how much has been studied about the finite functions linear ODE where Hegel's order called n is arbitrary and first D are fixed? Okay, and do you mean not Q still character 0 or finite fields? Right. All right. So before discussing John's question, let me also talk about Sida's comment. Yeah, we never thought about the situation when the coefficients are not in are not in Q. I mean, are not algebraic. But of course, that it's okay to think of D-finite series when the coefficients are in like a positive characteristic or function fields.
Yeah, I wasn't sure what kind of interesting things Alexei was after, so I wanted to clarify, but
I mean, of course, in a characteristic P, you cannot talk about the exponential function. I guess.
yeah, we can still talk about other things and how, in any condition of how f would be rational or algebraic. So that's why I asked. And isn't the looking at for characteristic 0 isn't looking at Q enough anyways?
Q bar. If you look at characteristic 0, but then at some point you realize that everything is defined over a finite Lie-generated field, and you can do specialization to reduce to the case of Q bar.
Okay, yeah, that makes
but
sense.
But if you are over function field, then you can also certainly talk about the height. There's a height function for function field. And my guess is that maybe certain things will go through in that setting. Yeah, we didn't think about those situations, but maybe it's possible.
Yeah, that's okay. Thanks.
And now John's question is about how much has been studied about D-finite function linear ODE where highest order n is arbitrary. First D are fixed. I also don't know this very well, so maybe if there's an expert about linear ODE in the audience, they can answer this.
I asked this because solving linear ODE, everybody writes linear ODEs just with the first initial and D plus 1 terms up through Dth order. But when you actually go to solve it, you're solving. If you want to solve it, you're solving for the nth coefficient or something. If you're writing this out as a power series, where n is arbitrary, n is bigger than the order D. You use the letter D for the order for D-finite functions. So I'm just saying that's what my interest in that, because you express all infinitely many coefficients in terms of the first D coefficients. I mean, you have to practically,
But then what's the question exactly? So you fix the initial conditions, you fix the equation and what you would like to have?
I was just curious about whether property, how much people have actually studied linear differential. Well, I'm really just asking how much people have studied linear differential equations where they study where the highest derivative is sort of arbitrary, and you're not worried about right. And the first derivatives are 0 through D minus 1, but the highest one is arbitrary. Everyone just assumes, right, or when they talk about linear differential equations, they're just analyzing the first D consecutive orders. Okay, they write the differential equation in terms of just the first 0 through D. He used the letter D for the order. I was just curious about how much people have studied it, where the highest order is not consecutive. It's not, it's not just the first D plus 1 or D consecutive orders or derivatives. Because it comes up, as I say, in practical application of trying to actually solve a linear differential equation. At least it comes up in my work. So,
well, I guess in principle it's in principle, it's the you have all the consecutive derivative, I guess, but now the coefficients, a lot of coefficients are zero. That's what you mean?
No, I just said no. I'm talking about the highest derivative appearing in the differential equation being non-consecutive. You know, I guess in well, if you're looking at D-finite functions, you wouldn't. You're actually looking for. See, in my work, I'm actually trying to compute the differential equation given known properties of the function. So. So technically, I'm actually trying to compute a differential equation, and that's why I'm trying to compute what the highest order is in terms of the first 0 through d-1. When you're studying D-finite functions, it's natural to just try to find, look at the differential equation of smallest order that it satisfies. So, so maybe my question wasn't all that good, but I just was trying to, I guess my point was just to sort of break out of the habit of constantly studying differential equations where they're always presented in the first consecutive, the first consecutive derivatives, from 0 up to n. That's all.
I see. Yeah, sorry. So more from the arithmetic point of view, and in that setting, people usually consider like algebraic coefficients, and they might reduce mod p or things like that, more than to compare with.
Understood. Okay.
Yeah. All right. So. Yeah, there's a comment and question from William. So conceptually, it seems the height is a more root way to compare the rows of functions to a class of function. Are there other classes that might have a similar concept of height? Well, to talk about height, you can talk about you have height for algebraic numbers. So that's probably the most interesting case, but they also have height for function fields, for algebraic functions. So you for example, you can consider K to be any field, and you can have the height function on this field, and you can also have the height function on this algebraic closure of this field. But if you consider like a random function, like a logarithmic function, exponential function, or things like that, they are not algebraic, so there's no height on those functions, I'm afraid. But as I said in the seminar, that there are other classes of power series that are interesting, like the result of Adamczewski and Bell about Mahler function. So they also prove some similar height gap principle for Mahler function with algebraic coefficients. I hope it answers the questions.
Okay.
Right.
Okay, thanks.
Yeah, thank you. And yeah, maybe I ask short questions. So does any of this work in nonlinear case? If I have nonlinear differential equation, can I hope for something, or there may be arbitrary coefficient growth?
Does D-finite imply linear equations?
At least in one variable. In multi-variable situation, you have a bunch of equations. Like you require the partial derivative to generate a finite dimensional vector space. So you're going to have a bunch of.
I see. In that case, so it's always linear then.
Yeah, but they're always linear. That's right.
Yes, so I'm asking about like differential algebraic functions, right? The next class. Do you expect anything interesting like this happen there?
Okay,
We don't.
the first I never thought about this, but yes, we certainly expect interesting things because the general belief is that if you have interesting condition, then there should be an interesting constraint or conclusion about the coefficients.
Okay, great.
So if you have
Yeah.
any specific examples, then maybe you can look at it and see what kind of height rows or any other arithmetic properties that might be interesting. Yeah.
Well, no, I mean, you can start with just first order equation, x prime is equal to f of x. Right? So what can I say about its coefficients of its power series solutions? Maybe it's trivial question. I actually don't know, but the coefficients will satisfy certain complicated relations of high order.
The best way to guess is to start from like x prime equal to f of x, and if you can somehow you see how the Taylor coefficients, if they satisfy certain like recurrence relation properties, then you can guess how the height rose. Yeah, so I guess it really depends on f, but
yeah. So what I was meaning is f is a polynomial.
f is a polynomial.
Yeah, but not linear.
Prime is f of x. Well, of course, you know, if x prime is x squared, and it what's that? So minus 1 over x is c or something. Huh.
Yeah, so here you get like rational function more or less, I think.
Yeah. So I would say that well, it probably depends on f, but so one way to find out is like to have like x is a0 plus a1t, and you can try to figure out like from this equation what kind of relation you have among the AIs. So, you know, among the AI, and from this relation you can see whether how the AIs how they roll. And of course, it really depends on f.
Okay. Suppose you have a differential equation and you have a power series solution. When you plug that in, don't you get a some relations, algebraic relations among the coefficients? So shouldn't we just take the ideal generated by those equations, and then maybe see when can we have a height function?
So the space you are talking about is the space of the coefficients, and then you consider like the ring of all the possible coefficients quotient out the relation.
Right.
Yeah, but
that must be satisfied in order to satisfy the differential equation.
Yeah, but this will be more or less the differential ideal changed by the equation up to like factorials.
Why differential ideal?
Yeah, this is probably the differential ideal. Yeah.
Okay, all right.
Probably isomorphic to that. If
well, isomorphic, yes. Like if you write instead of ak over k factorial, then I think ak's will satisfy the differential ideal. The equation. But yeah, okay, yeah, I see your point. So yeah, you should just look at the coefficients and yeah, try to define the relations recurrently. Okay, I understand. Any other questions, comments? Okay, then yeah, let's thank the speaker again. And in a week we'll have a talk by David. So we have please join us.
Thank you.
Wonderful
Thank you.
presentation. And thanks to
Thank you. Thank you.
Thank you.
Good day.
All right. Thank you, everyone.